Here we're going to talk about the various ways we depict molecules and the way we can draw them. So it's very important for us to be able to accurately describe the way molecules are connected, the way they sit in space, etc., so that we know how they react, we know the various properties, we know the energy of the molecule, whether it's a preferred state or if, again, it's going to want to react with something, and maybe how that reacts. So, like I said, it's very important that we have a good understanding of stuff like Lewis structures, for example. So we should have a good idea of Lewis structures. This is all review. We know how to draw Lewis structures, we know how to interpret them, and first we're just going to start off with what are some of the things that Lewis structures provide us with. So Lewis structures give us, obviously, the connectivity. So we can see which atoms are bonded to which atoms. We can denote that by the bonds there. Other things, we can know things like bond order or multiplicity. So from these Lewis structures, not just the bonds, but what bond order? Is it a double bond, a single bond, a triple bond? So that's one thing we can get. We can also get lone pairs on various atoms. So I'm sure we're all guilty of being a little lazy and not including the lone pairs, and even so, we still know the lone pairs are there. If I hadn't drawn them on the oxygen, you should be able to infer whether it's as soon as you saw the molecule, or if you had to think about it, you should know that those lone pairs exist, whether I drew them there or not. Sometimes it's annoying to have to draw all 6 electron, or all 3 lone pairs on halogens. So a lot of times you don't include them. But again, it's important that we can identify that they're there, even though we don't draw them. And lastly, something as obvious as the elemental composition. So we know that, okay, what elements are here in this molecule? It's very, very explicitly drawn here. So these are some of the things Lewis structures give us. However, they do give us, they leave us with a lot of questions as far as things such as three-dimensional geometry. We're forced to infer the bond angles and then, or thereby the molecular geometry of these molecules, since we draw them in the plane of the board. We don't know just based on this structure alone. But again, we should need to have a good idea of hybridization, how that leads to various bond angles, and then how that leads to geometry. So all this should be review, but yeah, and we can also have odd circumstances with various molecules. What I'm drawing here is what we call a methylene intermediate. And again, this is just jargon. Eventually you'll need to know it, but I'll write it out here. But yeah, so things like this, we know that carbon always has 4 bonds and no lone pairs, but in a reaction, that's, if it always had four bonds and no lone pairs, then how would things react with carbon, right? So so here we have an intermediate. It has the 2 bonds, the 4 bonding electrons. It has our 2 non-bonding or lone pair electrons to satisfy the 6 valence electrons in carbon. The 4 valence electrons in carbon. Wow. Okay, so so here's just an example of Lewis structures wouldn't give us this, because Lewis structures are drawn based on very rigid rules that we draw out the bonds first, then add lone pairs, and we wouldn't know to draw things like this intermediate here. So it leaves us with these questions, and or information that we aren't directly given by the structure. So that's why, as you might guess, we need various ways to depict molecules in order to especially determine things like the three-dimensional geometry. That's going to be very important. So, like I said, we're going to need different ways to draw these molecules, especially depicting them in 3 dimensions. So, as we know, molecules that contain single bonds are rapidly rotating about those bonds. For example, this double bond here, there's no rotation here, but there is rotation about this single bond, about these bonds. So that's why these molecules have energy, because they're rotating, or at least kinetic energy in that sense. So I'll go ahead and erase this, but we're going to need different conventions in order to depict the rotation in a molecule. Let's see, so first way we can do it is with wedges and dashes. So if I were to draw that same molecule, I could draw everything here. Just like this. But I could include wedges or dashes to indicate whether this bond is going out of the board or into the board, or if it's in the plane of the board. All of these that are just depicted with normal bonds that are just lines, these are all in the plane of the board. Wedges, like this, these are all going to be out of the board. So these are coming out at us. And things like this, which are dashes, these are going into the board. So we can think of this as we're almost kind of looking at it from this direction. We can see all these things in the plane of the board. We know this one's out of the board, this one's into the board. So this is more realistic of what this molecule looks like in space. And I'll draw what I had as the Lewis structure up here, just for reference, and we can see how I had no idea that these bonds were not in the plane of the board just by this structure alone. So another way I could do it is what we call a sawhorse projection. And with this, it's like its name, it's a projection to where things that are behind are further into the board, and the things that are up front are closer to us. So it's about as simple as we can get here. I'll go ahead and draw a different molecule. Here I'll draw just a 2-carbon molecule. But as you can see, things like this is the front carbon. It has 3 hydrogens attached to it. It's also attached to this carbon, which is in the back. And so we can think of this molecule just as this molecule here, which I'm going to depict with the Lewis structure. And we can see how these things don't look anything alike. And the reason I show it like this is because now we have an idea of maybe this is good for showing the conformations of various groups that are attached to like carbon atoms, the orientations in space, not necessarily whether it's coming into the board, out of the board. It's more focused on these groups that are around the carbon and which ways they're rotated, which ways they're oriented in order to determine the lowest energy states. And kind of extending off of that, we have what we call a Newman projection. It's also going to depict rotation, and this way we draw it as a circle like this, and basically what we have here is we're looking through a bond. So if you can imagine this sawhorse projection, and this is our eye here, and we are looking this way, right through this bond here, you can see that. So you can see we're looking right through this bond. Did not mean to do that. Okay, so what we're going to see is we're going to see these hydrogens here in front, and we can just infer that this is going to be our central atom. And again, if we're looking this way, we cannot see this back central atom. We cannot see the bond. We're looking through it here. I'm just going to depict it as this point, and you can see that, okay, there's space here. We can see this hydrogen up here. We're going to draw it in the back, and as well as these hydrogens here, we're going to draw in the back. And this is what we refer to as a Newman projection. And you can see that the things in front of this circle, in front of the circle, that you can see the lines are going through right here, these are in the front. The things that are kind of coming out of the back of the circle, these are the hydrogens in the back. So these two are similar in many ways, because they both show the arrangement, if you will, of atoms like hydrogen around like a central atom here. So for example, this is just showing the hydrogens here. I could have a different group instead of hydrogen, like if I replaced this with a chlorine, obviously this hydrogen would be replaced with chlorine. So, and you can see how maybe this one down here, if I replaced this with a bromine, this one down here would be replaced with bromine. So these are analogous in many ways. The wedge and dash is very commonly used to depict molecules because we can really tell the 3D geometries. But as a general rule of thumb, we don't want to just abandon Lewis structures, because when molecules get complicated, when we have 10, 12 carbons, we have ring systems, it's complicated to draw out all these things. This is pretty specific. So we're looking through one bond. We're only going to show, as you can see, 6 different groups attached to the 2 carbons we're looking at. Here, if we want to draw a whole molecule with the wedge and dash, that gets complicated, and that's going to take time. So we don't want to just abandon Lewis structures. They're very helpful in many ways, but as far as our 3 conventions for depicting rotation within a molecule, these are very important, and you need to be comfortable drawing molecules like this and also interpreting what the Lewis structure might be, or just what the molecule is based on these things. So I would suggest being or familiarizing yourself with these concepts so that you have a good understanding of how these molecules look in a way that Lewis structures just can't provide sometimes.